This is Module 5 and involves chemical reactions and quantities. In our textbook, Module 5 is Chapter 5. That's in the 10th edition of the textbook. We're looking at different changes, physical changes such as changing state. Here we see liquid water melting, or ice melting, liquid water freezing, and water turning into steam, steam turning into liquid. In a physical change, the composition is unchanged, meaning it's still water, it's still H2O, whether it's in the solid, liquid, or gas state. It might change shape, but physical changes tend to be relatively easy to reverse. Chemical changes, here we see a burning match. A burning match would be an example of a chemical change. A chemical change creates a new compound. That's the main way to know if you've got a chemical change, is something new with a new chemical formula produced. Since new compounds may have different colors, you may see a change in color when you have a chemical change. If one of the new chemicals created is a gas, you might have evolution of a gas. And very often, because chemical changes involve the breaking and forming of chemical bonds, you can have a change in temperature. If the change in temperature is releasing enough heat, the chemicals that are produced may actually begin to glow. You can have a production of light, as we do in this match. We have production of light as the chemicals get hot enough to glow. Chemical changes are less easy to reverse than physical changes in general. We have some examples on this page, and we can ask ourselves, are we looking at a chemical change or a physical change? The main question to ask is it still the substance you started with? For example, melting ice or freezing ice cream. We still have water before and after the melting, and so it's still the same substance, so it's physical. When a car rusts, the iron in the steel of the car turns into iron oxide. So it's not the same substance. It's a chemical change. If I boil water, that's a physical change because even the steam is still H2O. If I crack open an egg, that's not a chemical change. The egg parts are still made of the same chemicals they were before you broke the egg. When a brunette turns blonde after a summer in the sun in the pool, the change in color might indicate that some of the chemical dyes or the natural pigments in her hair are changing chemically from the action of the chlorine in the pool and the energy from the sun. Fermenting grapes, the sugars in the grapes turn into alcohol, so that's a chemical change. If I put vinegar and baking soda to make a volcano model, the evolution of gas produced indicates that I'm making a new substance. The glow stick produces light, so that it kind of indicates that we're probably looking at a chemical change as well. However, toward the upper right here, boiling ethanol. Boiling is just the conversion of a liquid to a gas. Dissolving sugar in water to make rock candy. The sugar is still sugar, the water is still water. There's no chemical change. If I soak a chicken bone in vinegar and the vinegar acid removes the calcium, there's probably a reaction between the calcium in the bone and the vinegar. But if I simply mix some Kool-Aid mix and some sugar into water and make a cool drink, mix up a pitcher of cool drink, In that case, I'm just likely mixing things and they're still the same individual substances, they're just mixed. Burning a match we showed earlier is chemical. Cutting a piece of paper, it's still made of paper. Wouldn't suggest cutting dollar bills, but if I squeeze an orange, I'm simply separating the liquid from the orange, not making a new substance. That's physical. Frying an egg does result in some changes to the protein structure of the egg because it goes from a liquid to a solid. So there could be some chemical changes during the frying of an egg. You might remember from Chem 1 that we had 5 types of reactions. Let's review those 5 types. Chem 2 might use slightly different names for them, but these are the names that will be used on the book problems and in the quizzes and tests, or quizzes rather, over types of reactions. Combination, 2 or more chemicals come together to make one chemical. Decomposition, a chemical breaks down into 2 or more chemicals. Single replacement, one element replaces another element in a compound. And double replacement, 2 elements trade place in a compound. And then combustion is when a hydrocarbon reacts with oxygen to make carbon dioxide and water. Let's go over these one by one. Combination, also known as a synthesis reaction. 2 or more elements form a product, or simple compounds combine to form a product. If you burn magnesium, the magnesium plus oxygen makes magnesium oxide. Sodium metal and chlorine gas react to make sodium chloride. Sulfur trioxide and water making sulfuric acid. All of these have the general format of A plus B yields AB. So they are combination reactions. Decomposition is simply the reverse of the combination reactions. One substance splits into 2 or more simpler substances. For example, if you heat mercury oxide, it'll become liquid mercury and give off oxygen gas. If you heat potassium chlorate, it'll become potassium chloride and give off oxygen gas. Both of these would be examples of decomposition, AB making A plus B. In a single replacement reaction, one element's taking the place of a different element in a reacting compound. Zinc is a fairly active metal. It will react with an acid such as HCl. The zinc will replace the H in HCl, making zinc chloride. Since the H is replaced, it's now alone and it forms H2. Iron is more active than copper, and iron will replace copper in copper 2 sulfate, making iron 2 sulfate and releasing the copper metal. So these have the general format of A plus BC yields AC plus B. In a double replacement, you have 2 species in the reactants that are going to change places. Sometimes these are precipitation reactions, such as silver nitrate and sodium chloride, both aqueous, making silver chloride solid, which will precipitate out, plus sodium nitrate. Notice the silver has replaced the sodium in sodium chloride, but the sodium replaced the silver in silver nitrate. So now it's silver chloride and sodium nitrate. Another possibility is to generate a gas from part of one chemical and part of another. For example, zinc sulfide and hydrochloric acid, the hydrogen and the sulfur, the hydrogen from the HCl, the sulfur from the zinc chloride, could get together and form hydrogen sulfide gas, which would be evolved as a gas. That would leave the zinc and the chloride as the only 2 chemicals left, and they would then combine to make zinc chloride. So these have the general format of AB plus CD yields AD plus CB. Combustion. Combustion is when you have a carbon-containing compound that's burning in oxygen, and the general format is it produces carbon dioxide, water, and generally energy. This is one of our main sources of energy, is the burning of hydrocarbons such as methane or natural gas, CH4 plus 2O2 yields CO2 plus water, 2 waters. Energy is produced, and that's how we make our burner work in the lab. You can even predict the number of carbon dioxides that will be equal to the X in the hydrocarbon, and the number of waters will be Y over 2. So let's practice. We've got our 4 choices: combination, single replacement, decomposition, and double replacement. We have barium and nitrogen coming together to make barium nitride. So that looks like A plus B yields AB. So A should be combination. In B we have silver and hydrogen sulfide becoming silver sulfide and replacing hydrogen. So B looks like single replacement. In C we have silicon paired with oxygen and hydrogen paired with fluorine. After the reaction, silicon is paired with fluorine and hydrogen is paired with oxygen. So that looks like a double replacement. Another double replacement: lead paired with chloride, potassium combined with sulfate. After the reaction, potassium is now paired with chloride and lead is paired with sulfate. So that's a double replacement. In E we have one chemical breaking down into 2, potassium carbonate breaking down into potassium oxide and carbon dioxide. So that would be a good example of decomposition. Check our work. Looks like we got them right. Here is a topic we typically did not go into any detail on in Chem 1. In chemical reactions, very often there is a transfer of electrons from one reactant to another. Reactions of this type are called oxidation-reduction reactions, or redox for short. The chemical that is losing electrons is said to be oxidized. Oxidation is loss. So the words oil and Leo, oxidation is loss, loss of electrons. Oxidation, LEO, loss of electrons, oxidation. Oxidation is lost. So we have zinc solid losing 2 electrons to become zinc ion plus 2. At the same time that one chemical is losing electrons, the other one would be gaining electrons. Since electrons are negative, to gain electrons is to reduce your charge, so we call that reduction. We might remember it by the word Rig. Reduction is gaining electrons, or GER, gain of electrons oxidation, or gain of electrons reduction. Now you might think, well, how am I going to remember these words? Oil, Leo, Rig, GER. GER isn't even a word. But if you think about it, oil rig are 2 words that typically go together. An oil rig is something that drills oil wells. So oil, oxidation is losing. Rig, reduction is gaining. Might help you remember which is which. The other saying is Leo the lion goes GER. So Leo is the zodiac symbol for the lion, so Leo the lion goes GER. Of course, typically lions roar instead of go GER, but then that wouldn't explain loss of electrons being oxidation and gain of electrons reduction. Here we have copper plus 2 being reduced. It's gaining 2 electrons, the same 2 electrons lost by the zinc metal, and so you end up with copper solid. So to track the gain and loss of electrons in reactions can help us understand oxidation and reduction. So oxidation always involves loss of electrons. It may involve addition of oxygen, hence the term oxidation. Very often when oxygen reacts with something, that substance will lose electrons. It may also involve the loss of hydrogen. Reduction always involves the gain of electrons. Sometimes that also means a loss of oxygen or a gain of hydrogen. Now let's take a look at these three reactions and see if we can identify each one as oxidation or reduction. Tin metal becoming tin plus 4 electrons. In this particular reaction, it looks like 4 electrons have been removed from the tin atom, leaving the tin with a plus 4 charge as an ion. And so if we think about oil rig, oxidation is losing, reduction is gaining. In this case, the tin is losing 4 electrons, and so we would call a oxidation. If iron plus 3 gains 1 electron and becomes iron plus 2, we would say that's reduction, because reduction is gaining, oil rig. Likewise, if Cl2 gains 2 electrons to become 2 Cl minuses, that's also gaining electrons, so that's also reduction. Oxidation, reduction, reduction. Let's talk about chemical equations. Chemical equations are like a recipe. They tell you how many of each reactant to put in, and they will also indicate how much product can be formed. For example, if you want to make a cake and it requires 2 eggs, a cup of water, and a box of cake mix, then you could write a chemical equation for it that said 2 eggs plus 1 water plus 1 cake mix. That would be a combination reaction. Produces E2WCM, E eggs, W water, CM cake mix. So that would be a balanced equation. Of course, we use it to describe what's happening with the atoms and molecules. Let's say that I'm going to burn some coal. Coal is carbon. I use oxygen to burn it, and it produces carbon dioxide. One requirement to make this chemical equation is that the same number of atoms of each type must be on each side of the reaction. So on the left side, we see 1 symbol for carbon, indicating 1 atom of carbon. The O2 has a little subscript 2, so that indicates 2 oxygen atoms. So the left side has 1 carbon atom and 2 oxygen atoms. On the right side, they've combined to make carbon dioxide, but carbon dioxide in its formula has 1 carbon atom and 2 oxygen atoms. And so the reactant atoms equal the product atoms. So to start out on our learning how to balance equations, let's start by just stating the number of atoms of each element on the reactant side and the product side. In other words, let's learn to interpret the chemical formulas. In letter A, P4 solid plus 6Br2 liquid yields 4 PbBr3, PBr3 rather. P4 indicates there's 4 phosphorus atoms, 6 Br2s. A Br2 has 2 bromine atoms. If there are 6 of those, then that would be 12 bromine atoms. 4 PBr3s. There's only 1 P in PBr3, so if I have 4 PBr3s, that's 4 Ps, 4 phosphoruses. Br3 means there's 3 bromine atoms in a PBr3. So if I have 4 molecules of PBr3, that's a total of 12 bromine atoms. In B, we see 2 aluminum atoms plus 2 iron atoms and 3 oxygen atoms. making 2 iron atoms plus 2 aluminum atoms plus 3 oxygen atoms. So learning how to interpret the subscripts and the coefficients. So notice in both cases we do have a balanced chemical equation. There are the same number of each type of atoms on each side. So that indicates an example of the conservation of matter. The law of conservation of matter is an important consideration in chemistry. It says matter is neither created nor destroyed, so there must be the same number of atoms of each element on the reactant side as the number of atoms of each element on the product side. So since matter is neither created nor destroyed, all the same atoms show up on both sides of the equation. If you take 2H2 plus O2 yields 2H2O, on the left side I see 4 hydrogen atoms and 2 oxygen atoms. On the right side I see 2 waters. Water contains 2 hydrogens and 1 oxygen, so when you double that, that's 4 hydrogens and 2 oxygens. So it's indicating the law of conservation of matter. Okay, now that we know how to count the atoms, let's see if we can determine whether a particular equation is balanced or not. If I have 2HCl plus CaOH twice yields H2O plus CaCl2, I could check the hydrogens, chlorines, calciums, and oxygens on each side and see if they're balanced. 2HCl has 2 H's, H2O has 2 H's, but it does not account for the 2 H's in the CaOH2 on the left side. So there are actually 4 H's on the left and 2 on the right. So there's a case where it's not balanced. The Cl's are balanced. 2 Cl's, 2 Cl's. The Ca's are balanced. 1 Ca, 1 Ca. But there are 2 oxygens in CaOH taken twice and only 1 oxygen in the H2O. So the H's and the O's are not balanced in the first reaction. In the second reaction, we have 4 carbons on the left and 4 carbons on the right. We have 12 hydrogens on the left and 12 hydrogens on the right. And we have 14 oxygens on the left. And we have 6 plus 8, which is 14 oxygens on the right. So it appears to me the combustion reaction in the middle is balanced. 2HCl plus Na2CO3 has 2 H's. The right side has 2 H's as well in the water. 2 Cl's. There are 2 Cl's because there are 2 NaCl's. 2 sodiums, 2 Na's. Also 2 Na's on the right. 1 carbon, 1 carbon. 3 oxygens, and if you look at the 1 oxygen in the water and the 2 in the carbon dioxide, you also have 3 oxygens on the right. So the first one was no, because the hydrogens and oxygens weren't balanced, and the second 2 were yes. So now we're ready to move on to actually balancing some equations, where we start by writing out the formula of each of the reactants and products. Put an arrow between, right? We list our elements. So we go through the elements one by one. It's good advice to always leave the hydrogens and oxygens till last, because typically you'll balance those in the end by putting a coefficient in front of water. We count the number of each atom, and we balance one atom at a time, starting from the top, changing only the coefficients. And when we get to the bottom and we've balanced all the atoms, we have a balanced equation. A balanced equation should always have the simplest ratio of coefficients. You get to the end and you find that your coefficients are all divisible by 2, go ahead and simplify. So let's take a look here at Fe3O4 plus H2 yields Fe plus H2O. We have some iron oxide and some hydrogen gas, and we're turning it into iron, metal, and water. If we look at the left side, it's 3 irons, 4 oxygens, and 2 hydrogens. The right side only has 1 iron, 1 oxygen, and 2 hydrogens. So the first thing we do is we put a 3 in front of the iron on the right side. That will equalize the Fe3O4's 3 irons and the 3 irons on the right. Now in the process of doing that, we did not change the oxygens nor the hydrogens, so we still have 4 oxygens on the left and only 1 oxygen on the right. So for that one, we would take water on the right and multiply it by 4. So now we have 4 oxygens still on the left, but by multiplying water by 4 with a coefficient, we now have also 4 oxygens on the right. That has taken the hydrogen, which was previously balanced, and thrown off the balance, because now we only have 2 hydrogens on the left, but 4 H2Os would mean 8 hydrogens on the right. So the last coefficient we need to add is a 4 in front of hydrogen. Now taking a look at both sides of the equation, 3 irons, 4 oxygens, 4 oxygens, 8 hydrogens on the left, and 8 hydrogens on the right. So we are happy to have balanced the equation. Fe3O4 plus 4H2 gas yields 3Fe solid plus 4H2O liquid. So that's an example of balancing an equation. So we could practice balancing these equations. Starting with the Mg, the magnesium, there's only 1 on the left and 3 on the right. So we might put a 3 in front of the Mg. We'll probably leave the N2 alone since there's 2 on the left and 2 on the right for nitrogen. So just a 3 in front of Mg should be enough to balance letter A. Letter B has 1 aluminum and 1 aluminum, but it has 2 chlorines on the left and 3 on the right. The least common multiple of 2 and 3 is 6, so that means I need to put a 3 coefficient in front of the Cl2 on the left and a 2 coefficient in front of the AlCl3 on the right. That balances the chlorines, but it does throw off the balance that we previously had for aluminum. We now have 2 aluminums on the right and only 1 on the left, so a 2 in front of the aluminum on the left would be appropriate. Letter C, Fe2O3 plus carbon yields Fe plus CO2. 2 irons on the left, I need to put a 2 in front of Fe. 3 oxygens on the left and 2 on the right. Well, that means I need to use that 3 to 2 least common multiple again. I'm going to go back and I'm going to double the Fe2O3 on the left, triple the carbon dioxides on the right with a 3 in front of the CO2. Now with that in mind, I have now changed the number of irons on the left to 4, so I need to go back and erase the 2 in front of the Fe solid on the right and make it a 4. Since I have a 3 in front of the CO2 on the right, I will need a 3 in front of the carbon solid on the left. So 2, 3, 4, 3 should be my balanced equation coefficients. Letter D only has 1 aluminum on the left, 2 aluminums on the right, so I need to put a 2 in front of the aluminum. The 3 oxygens on the right can be balanced by putting a 3 in front of FeO on the left, and then the 3 Fe's on the left can be balanced by putting a 3 in front of iron Fe on the right. So here's what those equations would look like with their coefficients that allow them to balance. Another consideration in reactions is the energy of reactions. Some reactions produce energy, other reactions absorb energy, but there's also a type of energy called activation energy, which is the minimum energy needed for the reaction to initiate. One thing we do when we strike a match is we take chemicals that are ready to react and we add a bit of energy due to the friction of the match dragging across the rough side of the match container. That friction heats up the chemicals enough to initiate the reaction. And that's because reactions occur when molecules collide. Let's say we were going to react a nitrogen molecule and an oxygen molecule as shown in the diagram at the right. N2 plus O2 are my reactants. Well, how are we going to get the N2 separated into nitrogen atoms? How are we going to get the O2 to separate into oxygen atoms? One way to do that would be to collide the two molecules with sufficient kinetic energy to break the bonds in the N2 and the O2. If the collision has the right orientation, as seen at the top of the curve of the graph, at the very top of the diagram, see the red and the blue are coming together with high amounts of speed. So that bumping together at that high speed is going to be enough to break the bonds and allow them to recombine as nitrogen oxygen plus nitrogen oxygen. N2 plus O2 yields NO plus NO. If the nitrogen and oxygen do not have enough kinetic energy, in other words, they're at too low of a temperature, because remember, temperature is how we measure the kinetic energy of molecules. If the nitrogen and oxygen have too low of a temperature, they won't react. They won't be able to initiate the reaction. They won't have enough activation energy. But when nitrogen and oxygen are heated to a high enough temperature, then their collisions can have enough energy to get over the activation energy hump, as seen in this diagram. And once they get over the activation energy hump, they can reform new bonds. And so basically, as we map the energy here, on the left it appears that the reactants are more stable and have stronger bonds than the products, because the reactants are lower energy than the products. But the highest energy is what is created at the instant of collision, because at the instant of collision the bonds are breaking. And you put in energy and raise the energy when you break bonds, but you get some energy back when you form bonds. So here we're putting in more energy to get up the hill than we get back when we come down the hill. We're putting in more energy to break the bonds in N2 and O2 than we get back when the NO and NO bonds form. So when a collision provides equal energy or greater than the activation energy, you can actually make a product. Here we see two diagrams. The one on the left indicates an exothermic reaction. I can tell that because the product has lower energy than the reactants. It takes less energy to break the bonds and make a collision occur to break the bonds than you get back when it forms bonds. And so you put in less, get back more, and so the overall change is energy comes out due to the formation of stronger bonds than the reactants have. That would be an exothermic reaction. The one on the right shows an endothermic reaction. I think we talked that one through on the last slide, how you're putting in more energy to break the bonds than you get back when you form the bonds. So if the products have lower energy than the reactants, then it's going to be exothermic. If the products have higher energy than the reactants, it will be endothermic. Exothermic means heat is released. The energy of the products is less than the energy of the reactants. So there's some energy loss. Heat then can be considered as a product in that case. Heat is produced, heat is released. In an endothermic reaction, heat is absorbed. The energy of the products is greater than the energy of the reactants, so heat is a reactant. Heat is added in the case of the one on the right, endothermic. One way to speed up a reaction that may be too slow because the reactants may not have enough kinetic energy or enough temperature to react is to add a catalyst. A catalyst can lower the activation energy, as shown on the diagram on the right, and by lowering the activation energy, the collisions do not have to have as much energy when the molecules collide and break bonds. And so a catalyst can speed up reactions simply by lowering the activation energy. Catalysts always increase the rate of a reaction. They lower the energy of activation. Catalysts are not used up. They're not a reactant nor a product, and so you always have the catalyst to do another reaction after participating in a particular pair of chemicals reacting. The catalyst can then be reused again to help another set of chemicals react. Now there is a required reading on Cobra about equilibrium. That is an extra reading that is because the textbook does not go into equilibrium. This is an extra reading that you should read from Cobra. Another thing you should also look over is the section on using your calculator, because we are going to be moving into moles in the next unit, and moles require you to use your calculator to show scientific notation. We're going to talk briefly about chemical equilibrium, but you should also, it says down the bottom, see Angel. Angel is actually what the Cobra now is, and so Angel was what we called the old learning system for Parkland. It's now Cobra, so if you replace the word Angel with Cobra, see Cobra for additional required reading. Chemical equilibrium. Some chemical reactions occur both forward and reverse directions. For example, if two SO2s and an O2 could collide and get over the activation energy hump and create two SO3s, at the same time, two SO3s might also be able to collide and turn back into two SO2s and O2. So the forward reaction and the reverse reaction are written here. However, we could combine those into a single reaction and simply show the arrow going both directions. If you see a double arrow going both directions, that indicates an equilibrium scenario. So we see the forward arrow representing 2SO2 plus O2 yielding 2 SO3s, but the reverse arrow indicates that 2 SO3s could yield 2 SO2s plus O2. Typically what you'll have is a period of time that it takes these chemicals to reach equilibrium. At the point these chemicals reach equilibrium, the rate of the reverse reaction will equal the rate of the forward reaction. When the forward and reverse reactions are happening at the same rate, you will have changes occurring at the molecule level, but the overall amount of each reactant and product will stay the same, because for every 2 SO3s formed, 2 SO3s also break down to make 2 SO2s and an O2. And so over time there's no change. We've reached an equilibrium because the forward and reverse rates are equal. So here's a little attempt to diagram this. We see in the first circle O2s and SO2s. They have not reacted yet. They begin to react and they form SO3s. But you still have some SO2s and O2s left over. In the middle we see the equilibrium state. The equilibrium state will have both some SO3s and some SO2s and O2s. And that's because you're always running the forward and reverse reaction at all times. And so you have to have some reactant and some product at all times. You could actually reach that equilibrium state coming in from the right. You could start with all SO3s. And some of those SO3s would react to make SO2s and O2s, and you would reach the middle circle equilibrium case from the right. So you can come to equilibrium from the reactant side or from the product side. But once you reach equilibrium, you'll have a certain amount of reactant and product that will be the equilibrium amount. Sometimes you can have an equilibrium, but then the equilibrium can be upset by outside stresses. The Frenchman Le Chatelier stated his principle involving equilibrium that says when a stress is put on a system in equilibrium, the equilibrium is shifted to relieve the stress. So some possible stresses might be the addition of reactant. The addition of reactant should speed up the forward reaction, and so the stress is relieved by shifting to the right, making more product. Too much reactant to be at equilibrium means you need to turn some of that reactant into product. However, if you remove some reactant, you'll have too little reactant. And so you relieve the stress by shifting the equilibrium to the left to make more reactant. Addition of a product means now the stress is that you have too much product. You need to shift to the left to have less product and more reactant. Removal of product means you have too little product, and so you need to shift to the right to make more product. So when stress is put on a system in equilibrium, the equilibrium is shifted to relieve the stress. You can also think of heat as a reactant or product. In an endothermic reaction, heat is a reactant. In an exothermic reaction, heat is a product. So putting in heat can shift an equilibrium to the left or to the right. Also, removing heat by cooling a chemical change can also result in a shift. If we take a look at the first reaction up here, let's say we have 2SO2 plus O2 yielding 2SO3. The addition of oxygen or sulfur dioxide, the addition of a product, would actually mean that the forward reaction will run faster than the reverse reaction. We will say that the equilibrium is shifting to the right because more SO3 is being produced than is being used up. At some point, the amount of SO2 and O2 and SO3 will reestablish equilibrium once you've used up some of the extra reactant that you've added. So in the end, at equilibrium, you'll have more SO3 than you had to start with. Removing a reactant, such as removing O2 or SO2, will slow down the forward reaction. The reverse reaction will be faster than the forward reaction. If you're doing the reverse reaction faster than the forward reaction, you're making some reactant. You're shifting the equilibrium to relieve the stress. The stress was removing reactant. The shift is to make more reactant. If we're making more reactant, we say we are shifting left. If I add a product, add SO3, that will make the reverse reaction again faster than the forward reaction. So as that occurs, we use up some SO3 and we make some more SO2 and O2 until it reestablishes equilibrium. The stress was adding SO3, the shift was to use up some SO3. And the last one, removing a product. Removing SO3 will slow down the reverse reaction. Now the forward reaction is running faster than the reverse reaction, and so for a period of time until equilibrium is reestablished, you will be making SO3 faster than you're using it up, and so the amount of SO3 will go up. We took away SO3, so we shift the equilibrium to make more SO3. Le Chatelier's principle.